Welcome everybody to the second June session of the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the pleasure of having these three speakers. I'm sure that we will learn a lot from their talks. Our first speaker is Kseniia Kurishchenko, who is a PhD student from Copenhagen Business School in Denmark. And today Kseniia is going to tell us about clustering and interpreting via mathematical optimization. The floor is yours, Kseniia.
Forget. Sorry, yes. I hope you can hear me and see me, right?
Yes, we can.
Okay, thank you very much for inviting me and for introducing me. So my name is Kseniia, and today I'm going to present for you our joint work with Emilia Carrizosa, Alfredo Marin, and Dolores Romero Morales. And here you can see the title, Clustering and Interpreting via Mathematical Optimization. So here's the outline of today's talk, but I'm going to the motivation. So as you know, the machine learning methods are really accurate machine learning methods are seen as a black box, and with high accuracy, we lose some interpretability of methods, but we actually want to have interpretability in decision-making models, and there is several well-known references. You have already seen it during last talks, and people want to know what is going on inside the model and want to interpret the results. And I'm going to show you my research in this area. So I'm not going to discuss whole interpretability in whole areas machine learning, but I'm focused on clustering. And we can aim for interpretability in cluster analysis in two ways, post-hoc interpretability and joint clustering and interpretability. In first way, we do clustering by any existed method and interpret the results in the second stage. And there is some work done already here. And the second way, when we can do clustering and interpretability together inside one model. And there is also some work have already been done. So there is no common term for interpretability. And in this presentation, we will understand under interpretability such explanation that for each individual, we will know whether it satisfies or not to the explanation. And also we will consider several types of explanations in today's presentation, namely prototype-based and rule-based. And now I'm going to explain a bit more what is that. So prototype-based explanations. Imagine we have clusters, K clusters, and I individuals. So this is red and blue one. And also we have set of prototypes, which are the same individuals from these clusters. And our model will tell us who of these candidates to prototype is actually our face of our clusters. So our model will choose these two guys as representative individuals for whole cluster, red for red cluster and blue for blue cluster. And we call them as prototypes. In rule-based explanations, we have also clusters, individuals, and also features of characteristics of our individuals, for example, income and age. And instead of having set of prototypes, we have set of basic rules, such that, for example, age less than 50 or income more than 2,000. And the model has to combine them in such explanations which are combination of our basic explanations. And now our red cluster is explained by this explanation, and blue cluster is explained by this explanation. If you ask me how we choose this explanation, I will tell you that we are using true positives and false positives concept, namely, if individual I from cluster K, so red individual from red cluster, is explained by red explanation, so belongs to red prototype, then we call it like a true positive case. But if individual belongs to a blue cluster but explained by red explanation, then we call it as a false positive case. And the same can be true for rule-based explanations. And the main goal is to maximize true positives and minimize false positives. So let me go to the post-hoc interpretability. And as a data, we have dissimilarity measured between each pair of individuals, and also clusters are given. So clusters can come from other clustering procedures. And we purpose two mathematical optimization models here, inspired by classical location analysis problems. So we develop the covering model, and this model finds a prototype and also a radius, and explain each individual inside of this radius by this prototype. The partitioning model finds only the prototype and explain individuals by the prototype. So there is two models. Main difference of them is that in the public model, we can have individuals which are explained by two explanations prototype, or not explained at all. In the partitioning model, we have unique assignments, and for example, this guy was explained by red prototype because it's closer to red prototype than to blue prototype. And again, the closeness we understand in terms of similarity measure. Okay, here's the covering model, formulation, and we have in our objective function, as I told you, optimization of total number of true positive cases, and we minimize total number of false positive cases. We weighted by theta. Also, we have one prototype per cluster, some constraints for choosing radius, and also we have these two important constraints, which are telling us that we can control true positive cases and false positive cases in each cluster. So what does it mean? For example, we have clusters, and we want for sure to have 80% of true positives and 20% of false positives. Then we can do it by these two constraints. Okay, so the second model was the partitioning model, and again, as before, the objective function maximizes total true positives and minimizes total false positives weighted by parameter theta. Also, one prototype per cluster, unique assignment, and the same control of true positive cases and false positive cases in each cluster. So the two models are formulated as mixed integer linear programming problems, and I will show you the results in the numerical illustration section. So now I want to show you model with rules. As you remember, we used for this model rule-based explanations, and we still in the post-hoc interpretability. So now we are giving a set of basic rules such that we can split them into some groups, for example, features, and there is an example of that. So imagine we have some characteristics of our data, and we can construct some explanations within each characteristics. And this is going to be our basic rules. And our explanation, which model will do for us, it's a combination of these basic rules, such that we can control the length of these explanations, so we can choose at most a basic rules, and also we have at most one rule from each group. So, for example, we have the list of basic rules regarding to age, and here we'll choose for one cluster only one explanation basic rule from that. Okay, so here is the model, and as before, we maximize total true positives and minimize total false positive cases weighted by theta. But now we have slightly different constraints because we want to choose at most one basic rule by group, and also we control the length. For example, we have 10 features, but if we will have a very long explanation, it will less interpretable. Then it's reasonable to have here this constraint, and it's very important. And yeah, some other constraints. So this model contains only interpretability measure inside here, which means that we are not doing clustering here. But this model we can adjust and insert here clustering, and I will show you how we can do this. So now I want to show you joint clustering and interpretability. And just to remind you, now we don't have clusters, we will decide it in the model, but still we have the similarity between each pair of individuals. And voila, here we add additional term, interhomogeneity term, and also we have to add several such constraints and terms here. So now we minimize our interhomogeneity and still maximize total true positives and minimize total false positive cases. And as you can see, because X is our decision variables as sigma, here we have product of two variables, and we can linearize this product in a very clever way, such that, so we introduce some new variables and add some, change our constraints, but now we have linearity here. But still we have product of two decision variables here, and we can linearize it by four-step transformation. So this model can do clustering and interpretability at the same time, because we have these three terms in our objective function. But clustering term is very hard to solve because we consider each pair of individuals, and I will show you in the result, numerical section how we do this problem. Okay, so now I wanted to show you some numerical illustrations, and first I will start with this model with prototypes. And here's our real life data. This is Canadian climate data. So our data is these 35 curves of annual temperatures, and we consider the distance between two curves as Euclidean norm between two vectors, and also this data, as you can see, by different color grouped in 4 clusters. And now we want to choose our prototypes. So the covering model gives us these prototypes, and here the quality. Quality, I mean how many total true positives and false positive cases per cluster we have with these chosen explanations, and there's that quality. And here we can have the perfect clusters, which means that we have 100% of true positives and 0% of false positives, which is good. The partitioning model gives us slightly different results, but still the quality is good. And the second numerical illustration is about simulated data. We want to show the scalability of our model. As you can see, our original data is 3 clusters in two dimension, and the size of that is up to 1 million. But of course, we can't solve it directly. We do sampling. So we select uniformly some individuals and some candidates to prototype, and then evaluate obtained quality on the original data set. And here that quality. So total true positives, but true positives cases, false positives cases for sampled data. It's what we obtain when we optimize the model. And this is the evaluated quality on our original data. And as you can see, I colored by blue, which slightly worse than sampled result, but the difference is just 2%. So it's really close to the sampled quality. And there is also several cases when the obtained quality is even better than obtained on sampled data set. So actually we can scale our data, and we can handle large instances. Okay, so now I want to move to model with rules. And as you remember, I told you this model can be considered for post-hoc interpretability and for joint interpretability. And we are using here Haugen data, which is used for regression. But we will ignore response variables when we do clustering. And when we have to have given clusters, we will use this variable to construct clusters by considering different quantiles of this response variable. And as explanations, basic explanations, we construct such rules as here, where each threshold for numerical variables is different values of quantiles for these features. Okay, and here the result for post-hoc interpretability. So we consider several number of clusters with different lengths. So when we consider short length, namely 1, so it means that we choose only a basic rule, we can see that we obtain not so high quality, but it's expected. And quality in terms of true positive rate. And also here the false positive rate, and it's also sometimes not good, especially for when we have length 1. But this is the quality which we can obtain when we have given clusters. Let me show you the results when we do simultaneously clustering and interpretation. So again, because the data is quite large for clustering, because it's hard to solve. So we also do sampling as we did for prototype model. And here the results for original data set. And as you can see now, our explanations are almost perfect everywhere.
You have 1 minute.
Yes, thank you. So yes, so this is, as you can see, different with previous results. When we do clustering, we can adjust clusters in order to have better explanation, and it's shown here. Okay, so it was my results for the model with rules, and I introduced several models with prototype-based explanations and with rule-based explanations, where for rule-based explanations, we can do clustering simultaneously with interpretability. And for future line, we would like to strengthen our model's formulation and provide some math heuristic to do with large-scale instances in the second model. And yeah, our first model with prototypes is already on ResearchGate, and the second model will is coming soon. So thank you for your attention, and yes, I am.
Thank you, Kseniia, for your nice presentation. We will move the question till the end of the session. Okay. So our next speaker is Benedetto Manca. He's a postdoctoral researcher from the Università di Cagliari in Italy, and he's going to talk about binary classification via ellipsoidal separation. The floor is yours, Benedetto.
Thank you so much. I hope you can see the slides and hear me, hopefully.
Yes, we can.
Yes, perfect. Okay, so I'm Benedetto Manca from the University of Cagliari, and thanks for the introduction and for inviting me at this seminar. So today I will talk about a joint talk with Annabella Storino, Enrico Gorgone, and Antonio Frungioni about binary classification via ellipsoidal separation. So I will introduce two different definitions of ellipsoidal separation, and then I will define two binary classifier based on those definitions. So I'll start with the first one. So we consider two finite point sets in Rn and an ellipsoid S. And we say that S separates A and B if every point of A is inside the interior of the ellipsoid S, and every point of the set B is left outside of the ellipsoid. So this picture shows the situation we are considering. So what we want to do is to find the minimum volume ellipsoid S, which separates A and B according to the definition I just gave you. So to do that, we consider the points of A and B as labeled points. So label -1 corresponds to the sets A, and label +1 corresponds to the set B. And we started considering the standard SVM model with quadratic kernel. So we start with this model where the map phi is the quadratic kernel map, which map the point from the space Rn to an higher dimensional space. So why we do that? It's because the kernel trick basically consists in mapping the point from the input space, where the points are not linearly separable, and the map maps the point into a higher dimensional space where it is possible to find a separating hyperplane. And so this is more or less the situation graphically represented. And in the case where the map phi is the quadratic kernel map, we have that the pre-image of the separating hyperplane in the feature space is a quadratic surface. But as it is, we don't have any condition on the surface, and so it can be any quadratic surface, so paraboloid, ellipsoid, or hyperboloid. So what we wanted to do was to force the structure of the separating surface in the input space to be an ellipsoid. And in order to do that, we consider the symmetric matrix W, which is constructed from the variable vector W in the quadratic SVM model. And we observe that the expression phi x scalar W is equivalent to this expression with the matrix W, which represents a quadratic surface in the input space, which is an ellipsoid if and only if the matrix W is semi-definite positive. Therefore, if we add the constraint W, the semi-definite positive, to the previous model, we obtain exactly the model we want to solve in order to find an ellipsoid which contains the point of A and does not contain any point of B. So from this model, then we adjust it a little bit because we add the term log that of W in the objective function, which models the volume of the ellipsoid, and the term Frobenius norm of W, which prevents the ellipsoid to be degenerate, which means that it prevents the ellipsoid to have semi-axes which are too close to zero. And finally, we added the slack variables xi I for every point because we want to find a solution even if the two sets are not perfectly separable with an ellipsoid. So once we solve this problem, which is possible to solve because it's just an SDP problem with we can define our classification criterion, which in this case is just the trivial one. So once we have the ellipsoid S, we say that the point X of Rn is classified as a point of A if it's inside the interior of the ellipsoid, and it is classified as a point of B if it's left outside of the ellipsoid S. So after this, we started to run some tests on normal data set taken from the lib SVM library. But as you can see, the results are far from being good, both from the time, because our program is super slow, and also the solution, the accuracy of the classifier is not better, for example, than quadratic SVM, which is our first comparison, because we derived our model from quadratic SVM. So we stopped focusing on this normal data set, let's say, but we realized that it is possible to apply our classifier to the problem of edge detection in pictures. In fact, we run just only few experiments, so we still want to investigate a bit more this application, but we think it is promising because, for example, in this case, our model finds a better solution than the quadratic SVM model. So clearly we have to compare our model with other edge detection program, clearly, but it was already curious that it is possible to obtain a better solution than the quadratic SVM. For example, also visually, we can tell that in here, the edge are better than here because they are not continuous. So as quadratic SVM can't find a full line here or in general, every line. And also, this is another example. But yes, as I said, we still need to investigate. Maybe we can improve our result in this problem, but we think maybe this is the right application for the classifier we found. So now I move to the other definition of ellipsoidal separation. So now we consider two convex sets in Rn and an ellipsoid. And now we say that the ellipsoid S separates A and B if S intersects every segment connecting points of A and points of B. So now this picture shows the situation we are considering. So we want the ellipsoid basically in between the two sets. So as before, we want to find a minimum volume ellipsoid which separates A or B. And in this case, we consider A and B given by the convex hull of two finite point sets. And if we denote with I and J the index sets, the program we want to solve is the following, so we want to minimize the volume of the ellipsoid, where the second and third constraint is just mean that the points of A and points of B are left outside of the ellipsoid. And the first constraint is telling us that we want at least one point of the convex combination of AI and BJ to sit inside of the ellipsoid S. So as you can see, this program, it's difficult to solve because it is linear, since we are multiplying the variable S with gamma, which is another variable representing the center of the ellipsoid, and we're also multiplying S by Exige, which depends on the variable alpha ij. So we started to reformulate the problem in order to be able to solve it. And the first thing we did was to get rid of the center of the variable gamma, which represents the center of the ellipsoid. And to do that, we use the fact that every ellipsoid in Rn can be considered as the intersection of an ellipsoid in Rn plus 1 centered in the origin, intersected with an appropriate hyperplane. In fact, once we have the matrix G representing the ellipsoid in Rn plus 1, if we decompose the matrix G as followed, as showed in the slide, and we compute the quantities gamma and delta, we have the following fact holds, which means that the point 1x in Rn plus 1 belong to the ellipsoid G, if and only if the point x in Rn belong to the ellipsoid S gamma in Rn, where S is derived from the components of the matrix G. Therefore, we can replace the variable S and gamma with the variable G, and we don't have to deal with the multiplication of S and gamma anymore, because we only have G. G is an ellipsoid centered in the origin. Then the second thing we did was to model the volume of the ellipsoid S in a different way. And in order to do that, we considered this quantity B of S, the box size of the ellipsoid S, which is represented by the picture, which can be used as a measure of the volume of the ellipsoid, as you can see from the picture. And it is possible to represent this quantity using this SDP constraint, which implies that the trace of the auxiliary variable t is greater or equal than the box size of the ellipsoid S squared. And since the inverse of S is a feasible solution of this constraint, and it is the optimal value of this small program, we can model the volume of the ellipsoid by adding in the objective function the trace of the variable t and adding the SDP constraint showed in the slide. So if we put everything together, we obtain the final model that we want to solve, where we just add the slack variables beta, v, and w in order to be able to obtain always a solution, even if the two sets are not perfectly separable. And then we add the Frobenius norm of f in the objective function, which, similar to the other approach, is preventing the ellipsoid to be degenerate. So this is the final model. Still, this was a bit difficult to solve, but we realized that if we fix the variable alpha, the program reduces to an SDP program. And on the other side, on the other end, if we fix the variable g, the program reduces to a quadratically constrained program. Therefore, we thought about using a block Gauss-Seidel approach in order to solve the program, which iteratively solve the SDP program in the variable g. And once a solution of this is obtained, we solve the quadratically constrained program in alpha, where G bar is the solution of the previous program. So this is, yes, this is just the scheme of the algorithm we used. So we first start with the randomly generated values of alpha. We initially solve the SDP program in order to have an initial ellipsoid. And then we iteratively solve the quadratically constrained program and then the SDP program till the relative decrement of the objective value, function value, is less than a certain threshold that we chose. So, okay, this is just the algorithm. And just to show you how the algorithm works, here you can see we have two sets of points, the blue one and the red points, so A and B. And the green points represent the point Exige at the first iteration. So as you can see, when the algorithm starts, the green points start to align into a line, because in this case, the two sets are linearly separable. And the ellipsoid shrinks into, in a way that it contains all the green points, but none of the red or blue points. Because in this case, we didn't use any regularizing term. So in this case, the ellipsoid can degenerate into a line. But what happens when the 2 points are not linearly separable? Here we can see that, yes, we see these 4 points makes the two sets not linearly separable. And in this case, we see that the ellipsoid starts to shrink, but instead of continue to shrink indefinitely, it decides that it is better to keep these 2 points, and therefore these 2 points inside of the ellipsoid, and not misclassify them completely, because if these points will be on this side of the ellipsoid, it will be definitely misclassified. So at least this shows us that the algorithm is doing something quite smart, at least even in these cases. So once we solve this program and found the ellipsoid, we can define the classification criterion. And so given a new point z var n, we first say that z is separated from A with respect to the ellipsoid S if S intersects every segment connecting the point Z with points of A, And S intersect only some of the segments connecting Z with point of B, and vice versa, Z is separated from B. And then we say that Z is classified as a point of A if it's separated from B with respect to the ellipsoid S. Vice versa, Z is classified as a point of B if it is separated from A. The only problem of thing is that many points, for example, every point inside of the ellipsoid S cannot be classified because they are neither separated from A nor from B. And thus we introduced a third class in the classification process, which is the class of undetermined or rejected points. So, okay, so this is just how we compute the classification criteria. We just computed the number of segments which connect Z with points of A minus S, analogously for the segments connecting Z with points of B minus S. And then the classification score is defined as RA of Z and RB of Z, which is just minus RA of Z, which is given by this expression. And then we say that if RA of Z is close to 1, then Z is classified as a point of A with a certain degree of certainty. And vice versa, if RB of Z is close to 1, then Z is likely to belong to B. And for the third class, we have that if RA of Z and thus RB of Z is 0, then Z is a rejected point. So the classifier is not able to classify it as a point of A or B. So the fact is that we have this rejection zone, so the rejected points in the classification process, implies that we have to consider it when computing the accuracy of the classifier, because we don't want the classifier to reject too many points or every point and not be able to try anything. So what we did was to, for example, if we have a set of points that we want to compute the accuracy for our classifier, so we know if these points are points of A or points of B, according to a certain label, then our classifier assigns a label which can be minus 1 plus 1 or 0, because the point can be classified as a point of A, classified as a point of B, or rejected. And then when computing accuracy, also in the training phase for the classifier, we say that every time you reject a point, so every time you assign the label 0, you pay something, which is a fraction of the number of samples, where Xi is a constant chosen a priori, which can be a number in the interval 0, 1, half. So in this way, the classifier should learn that it's not convenient to reject too many points, if it's possible. So for this approach, I don't have any results because it's super slow even for small instances. So what we are doing now in order to obtain some results is to improving the speed of the algorithm, and we're thinking about using a column generation type heuristic. So the idea is just to consider only a subset of point Exige, start to solve the first SDP program, and then update the variable alpha ij for every I and j using the first ellipsoid, and then trying to find a criterion that says that some point Exij will not contribute in improving the next solution of the next SDP program, and then iterate this process until we consider every point Exij where we discard every point which is not relevant, let's say, in the improving of the solution. So for now, we're working on this. And yes, I think I'm done. Thanks for the attention.
Great, Benedetto. Thank you very much for your presentation. I will ask to the audience that they save their question till the end of the session. And now it's time for our last speaker, Marco Morucci. He's a PhD student from Duke University in the USA. And Marco will talk us about adaptive hyperbox matching for interpretable treatment effect estimation. Marco?
All right. Thank you so much for the introduction. Yeah, and today I'm going to be telling you about my work on treatment effect estimation. This is joint work with Cynthia Rudy, Sudeepa Roy, Alexander Wolfowski, and Victoria Orlandi. More on that at the end. But let's dive right into it. So why causal inference? Well, so causal estimates are increasingly used to justify high-stakes decisions virtually in all sectors. And so it is important that we provide decision makers with models that give them trustworthy estimates, but that are also interpretable and justifiable in terms of humanly readable decision rules. So this is sort of a theoretical summary of the treatment effect estimation problem for those who are familiar with it. In practice, we have a set of n experimental units, and there is a treatment T that is either assigned or not assigned to some of these units. So Ti is going to be 1 when a unit I receives the treatment, and it's going to be 0 when it doesn't. And so the idea here is that we're only going to observe the state that they're in when they receive the treatment. So we're ever only going to see unit I either with the treatments or without the treatments, but never with both. But really what we're interested in is what would happen if we didn't treat unit I. And so the problem of causal inference is sort of the problem of solving this unobserved quantity estimation problem. More practically, without sort of delving on theory too much, here is what we would like to do. So consider unit A here in the figure to the right. It's a male with a certain set of, age, height, and weight, and we give a treatment to A. As I just said, what we would like to know is what would happen to A if he didn't receive the treatment. Now, the main idea behind matching is that we would like to compare A to its identical twin who didn't receive the treatment. So again, in the figure here, this is B, right? But the problem is, very few people have identical twins that we can observe. And so we never really observe B. So what's the best that we can do? Well, the best that we can do is scour our data set for someone who didn't receive the treatment, but is close enough to A in terms of these features that we observe. And so here in the feature, in the figure, this is going to be C. And so matching, very simply, is the problem of identifying everyone's most similar unit who received a different treatment than the one that they got. So why would we do this? Matching is but one way of estimating treatment effects of the treatment on an outcome. But I would like to argue that matching is a desirable way of sort of figuring out what the effect of these treatments are because it's interpretable. And it permits greater accountability in high-stakes settings. So for example, a policymaker that wants to figure out if some sort of education policy is having a good effect on test score results in schools should be able to explain how the number, this difference in test scores that they got was obtained in the first place. And interpretability has all sorts of other nice features, including trustworthiness. And the main idea here is that matching is interpretable because the estimates that it produces are case-based, right? You can say to a decision maker that you came up with this number for the effect of the treatment because you looked at similar cases. You can point to where in the data you got your estimate from. So this is nice, but the problem that arises is what do you do when you have continuous covariates? So continuous covariates, right, in a probabilistic setting, the probability that you're going to find units that have exactly the same value of a covariate is very low. And so how do you then know who to match with whom? seemingly natural solution here is to coarse in continuous variables, to bin them, and to then form groups of units that are mashed together based on these bins that we're making. However, how do we know how much should we coarse in each variable? This is, I would say, a pretty natural question that arises in this setting. So how do we go about that? Well, consider this setting here, right? So what we see in the figure to the left is a variable x that we would like to coarse in on the bottom axis, and here's y, which is the treatment outcome on the top axis. This black solid line here is the relationship between x and y. And so ideally, what you would want is you would want to match together that are close, both in terms of x, but also in terms of f of x. What happens when you just pick a size of a box, and then just sort of match everyone in the same box? Well, you get these problems here, such as the one to the left, where unit 1 and unit 2 are matched together because you're close in terms of x. But in this area of the x space, the function, the sort of value of y in relationship to x varies very quickly. And so these two units should not be matched together. But you also get the opposite problem in the further to the right area of the x space, because now you have units that are further away in terms of x, but in this part of the covariate space, y varies very little, and so you can match them together and you're going to get people that look similar in terms of outcomes. So ideally, what you would want to do is something like what's in the figure to the right. You would want to make your coarsenings or boxes adaptively to the outcome function that you're interested in. So if you look here to the left, now we're making boxes that are very close together whenever y varies very quickly. And instead to the right of this figure, we're making boxes that are wider and further apart whenever y varies slowly. And we're sort of avoiding these issues. Cool. So then what are our takeaways from this is that the relationship between x and y, where again, x is the covariates that we're matching on and y is the outcome that we're interested in, should be considered when making these boxes or bins. And even so, you should think that there could be an optimal width that sort of takes both into account, but the fact that this is fixed across the whole covariate space is just not enough, because different parts of the covariate space should be binned according to the variance of y. All right. And so in this paper that this talk is based on, we want to solve precisely this problem by learning optimal coarseness of this continuous data that satisfy the criteria that I just told you all about. So how does the algorithm that we propose work? So the first thing that we're going to do is we're going to divide our data into two different sets. There's going to be a training set and there's going to be a matching set. Ideally, the training set is a smaller subset of the matching set, and the matching set contains all the units that we would like to estimate treatment effects for. So on this training set, we're going to fit a flexible machine learning model to predict potential outcomes for each unit in the matching set. So again, for each unit in the matching set, we're going to use the training set data to predict what would happen if it got the treatment, which here is denoted by y1, and what would happen if it didn't, which is denoted by y0. I'm going to create a nice little table with all our matching units and these predictions in it. And again, this can be done with your favorite machine learning tool. It can be a black box. It can be whatever you want. Step number 2, we're going to take all our matching units and construct a p-dimensional box, where p is the number of features that we have, according to these rules. Number 1, there need to be as many units as possible in the box. Number 2, the predicted outcomes from the previous stage need to be similar among units that are in the box. And number 3, the predictions that we get by averaging observed outcomes of units in the box need to be similar to the predictions that the machine learning model makes for the same units. And so as you can see that as we add units, sort of our potential box that we're making kind of restricts itself, and it gets to this optimal shape. Once we found an optimal box the way I just described, we just match together the units that are in it. And that's it. This is very briefly the algorithm that we have envisioned for this. Formally, the problem that we solve can be stated in a very general way, like in this equation, where essentially we want to find a box that minimize outcome prediction error, minimize variances of outcome in the box, and it maximizes number of points within each box. In practice, this is the objective function that we employ in our implementation. And these f hats here are the predictions made at stage 1 by the machine learning algorithm on the units in the matching set. And so as you can see, we're sort of trying to make the distance between predicted outcomes for all treatments of units in the same box as small as possible. And then on the right hand side of this minus sign, there is a term that controls how many units are in the box, so that we can maximize that number. So the good news is that this problem that I just showed you can be turned pretty easily into a mixed integer linear problem by adding a few constraints and shifting a couple of things around that I'm not going to show you in detail, but it can be done. And then you can just plug it into your favorite MIP solver and get a solution from that. Yet another good news is that you can pre-process this program in some simple ways to make the optimizer work quite fast. And so you can get a solution for a moderately sizable data set in a workable amount of time. However, in our paper, we also propose a approximate algorithm that is much faster. And again, I'm not going to go into too much detail on how this algorithm works, but suffice to say that the algorithm works somewhat greedily by essentially doing a direction-wise expansion for the box. So suppose that you have a unit that you want to match. You're going to consider each covariate on its own terms, and you're going to expand the box along the covariate or direction with the lowest predicted outcome variance. And then you're just going to repeat and slowly grow this box until a desired threshold is met. And in practice, empirically, we find that this solutions output by this model get pretty close to what a MIP solver would output in a much longer time span. Okay, let me give you a sense of how this performs empirically. So we took this data set, the Lalonde data set, which is a benchmark data set in causal inference matching application. The idea is the data set is that it comes with both a randomized experiment, which is the golden standard for estimating the effects of the treatment on an outcome, and other subsamples of data sets that are not from an experiment that you just match units to. And so the idea here is that we know what the true treatment effect that we should be getting is from the experiment, and we're trying to get as close to it as possible by matching. We have around 185 units that we need to find matches for, and we have upwards of like 15,000 units that we can choose from. We match on things like age, education, prior income, race, marital status. And the question that we want to answer in this data set is, what is the effect of a job training program on income after the training program? So does going into the training program actually lead you to better employment opportunities down the line? Okay, let me show you what happens in practice with this. So again, remember we have an experimental benchmark, and we want to get as close as possible to it with our estimate. We have two potential samples that we can choose our matches from, CPS and PSID. And so the experimental estimate is $1,794 US. And we want to get as close as possible to this. So here are a bunch of existing matching methods, and this is these are the estimates that they output. So sort of a naive method goes completely haywire, it gets nowhere near close. Something like prognostic score matching gets pretty close, actually. It's not too bad, though there is some variance. But AHB is actually the method that gets the closest by far in this example. As you can see, we're off by at worst $60 roughly, and so that's what I think is a pretty good sign empirically that this is working well in this benchmark data set. Let me give you another intuition for why we are happy with the empirical results that we're getting. Recall that I told you that ideally adaptive bins would look something like what's in the figure that I'm showing you here. And these are the bins that AHB outputs on the data from Lalonde. And so just by looking at this figure, I can see that this is pretty close to what we were trying to achieve theoretically. And so it's telling me that we're moving at least in the right direction towards solving the problem that we want to solve. A couple more things. I started by telling you that I like matching because it's interpretable, and our matches are particularly interpretable. Here I'm showing you matches made with a different method, propensity score matches, versus our method. So this is the unit that we want to match. So this is a 22-year-old, white, unmarried, no high school degree person with no income. And these are the matches that we find by matching with prognostic score matching, which again is a benchmark sort of existing matching method. In orange, you see all the covariate values of units that are matched to it that are just very different from the treated units that we want to match to. Maybe the treatment effect that we get out of this group is close to the one that we would like from the experiment, but in practice, we match to units that are quite different. We don't really know how to interpret these units that are matched to our treated unit. With AHB, instead, we find that we match units that are pretty similar to the treated unit that we started with. And so this match group, is very interpretable. I feel like even by a non-expert, you can just look at it and see that you are comparing people that are similar in terms of the covariates. Let me give you one more example of interpretability. AHB permits you to create interactive outputs that kind of look like this. So this is a simulated data set in which there are two covariates, x1 and x2. And I'm going to show you the boxes that our method creates for each unit. So as you can see, you can sort of hover on the unit, and it'll tell you the estimated treatment effect, but it also will show you the box that the algorithm found for that unit. And so you can visually debug your data pretty easily, right? You can look at this unit and say, well, this unit got got a treatment effect estimate of 0.06 because it was matched to these other units here. And you can also go in and look at the boxes made for those units. You can have visual sort of confirmations of your assumptions by looking at, where the data is denser, boxes are indeed smaller. Where the data is sparser, boxes are indeed larger. And so, again, I think that this is very easy to interpret visually. Let me conclude by pointing you to our website. This is the Almost Matching Exactly lab. I want to point out two things. Number one, if you go on it, you will see pictures of all my wonderful collaborators that have worked with me on this project. And if you go on our software page, there will be links to R and Python packages that implements all our software that I've described during this talk. And if you think it can be useful to you, I encourage you to download it and play with it and send us an email if you think there are bugs or stuff that you like or you don't like. But yeah, so that's pretty much it. In conclusion, I hope to have argued that interpretability of causal estimates is indeed important. And I hope that I have showed you that we can indeed use machine learning to produce interpretable and accurate matching treatment effects via matching. And that our estimates are very richly explainable in terms both of cases and in terms of covariate similarity. And thank you so much. And if you have any questions, I am very happy to take them.
Thank you, Marco, for your nice talk. Now we have a time for questions to any of the speakers. So feel free to unmute yourself or raise your hand or type your question on the chat. Daniel Alois, would you like to state your question?
Yeah, hello. Thanks for the talk and for the series of seminars. I'm in Canada, so it's really interesting to meet you people here from such long distance. I have a question for Kseniia presentation.
Yes.
Maybe I lost something, but from what I understood, you use the labels in the objective function in your mathematical optimization model, and I was curious about that. Maybe I missed some part, but usually when you use clustering, it's in the case in which we don't have label data. So usually when you have label data, you go toward supervised methods like decision trees, SVMs, neural networks. So my question is more in the sense of regarding the main motivation for using this type of models that also include the true labels. I mean the true negatives, true positives, and things, and the variance into the model in order to use it in real.
Yeah. I hope you can hear me well. I apologize for some problems with my headphones. And yes, good question. And as I told, there is two ways. Actually, we can interpret given clusters, and why it's also important because clustering is something when we have a lot of different models of clustering, and usually what clustering does is just to minimize within distances of clusters or working with density. So actually clustering procedures themselves are not interpretable, and it also has some sense to interpret even result of clustering procedures, because actually there is the simple example. We can of course do clustering and then I don't know, apply decision trees on the labeled by clustering procedure data, but there is other options. And in my case with prototype optimization, sometimes we want to have a representative individual, and this is why we suggest these models. And in terms of clustering, cluster analysis, we can't interpret it so easy. So even post-hoc methods are useful. So this is my point, why it's important.
Okay. Well, I would have more questions, and maybe we can discuss by email.
Yeah.
I suppose you also have other questions from other people in the audience. But well, I'm gonna write to you, and we can maybe extend the discussion. Okay.
Thank you very much.
Thanks a lot.
Thank you.
Thank you. Are there more questions?
Could I ask Marco? So when you showed your methods, I saw you use notation of F function when you do this graph, and but actually when you do your algorithm, you are not using this F function at all, right? So you use rules instead of F function. And my question is, how do you think, is it possible to use this information about this F function to also construct this matching procedure or something like that?
Yeah, no, that's an excellent question. So the and I apologize for sort of the being overly notational there. It's an F instead of a Y because it's the expected Y. But anyways, our idea is that we want to construct rules that take the relationship between X and Y that's defined by F into account, right? And so in parts of the X space where F is very steep, right, where it varies very quickly, you're going to want to make rules that give you very, very tight intervals, right? Because you do, right, you do essentially want to be able to account for that variation. In the ideal no error world, F would just be stepwise, right? So that literally a box captures all of that variation. Yeah, I hope that answers your question.
Yeah, thank you very much.
Yeah, thank you for asking.
Thank you. Do we have more questions from the audience?
May I ask my second question to Benedetto? So I understood your idea for using ellipse for kernel function in first paper, but I don't know what's in second paper. Why do you want to separate two classes by ellipsoid, not by plane? What is the advantage of using ellipsoid? Could you explain?
Okay, good question, good point, very good point. So no, our idea is that the introduction of the rejected zone is quite important, because we think that if the classifier is able to be very accurate for the points left outside of the ellipsoid, and is able to tell us, okay, look, for this point, I really don't know what to say, so prefer to reject a point instead of misclassify it. It might be a kind of, there might be some application for this kind of behavior of the classifier. For example, for this is just an idea, we don't know if it works, but for a finance data set, it is good if your classifier says, I'm super sure that this will go bad or will go good, so you can invest in it. But on other points, maybe it's able to say, no, okay, I can't say anything about this point, so I won't say anything, so don't risk it. But when it's classifying a point, maybe it's a lot accurate. So you can trust him when he's classifying a point, but at least he's able to say, no, look, this point I don't know, so I don't risk it, and I'm not classifying, so because probably I will be wrong. So this was the idea, to use a convex set to separate other two convex sets, so that we have some point inside that are rejected, let's say, and they are not misclassified.
Thank you. Thank you. Now
You're welcome. Thanks for the question. Yes.
Thank you. We have time for another question. Okay. So if we don't have more questions, it's time to say big thanks to our three speakers and their three wonderful presentations, and also thanks to the audience. And see you next week. I recall you that we have Professor Gali Shmueli, but the time will be different. It will be at 10 a.m. Okay, so keep in mind. See you.
Thank you very much.
Thank you very much.
Thank you very much to everyone. Bye.
Bye.
Bye.